Yeah, so I was sitting over here finding myself getting a little bit nervous, which I rarely do before academic talks. My first thought was, well, maybe I'm nervous just because I'm actually talking to people that know more about this than I do. And then I thought, well, maybe I'm nervous because somebody might stand up and call bullshit on me. But we'll see. Anyway, so I'm going to talk about something called virtual aggregation. And this is the cast of characters that are involved. So a little bit of background on this. So, ISPs often, maybe increasingly so, for all I know, want to extend the life of an old router. And by an old router, I mean one that no longer has enough fib space to hold the DFZ. And a common and very effective approach is just to take old routers and then sort of reuse them as customer PE routers, and then just have these routers default to the ISP core. And as long as your customer doesn't demand the full DFZ in the BTP pairing, you're fine. But this takes you so far, and maybe for a lot of ISPs that's far enough. But a lot of ISPs want to shrink the fib even in routers that don't just serve as PEs to customer networks. So there's additional things that you can do, and one is you can just filter out more specific routes, and normally this is fine, and probably sometimes it leads to unreachability, but people do it. And another, if you're a lower tier ISP, you can just start defaulting to your transit ISPs. So one thing that you can do, and people do is just to use a 0/0. Default that to your transit ISPs, load balance between them, and just filter out most of the routes that you receive from them so that you don't have to put them in your routers. And, this is what it is. It leads to often non-optimal routes. It can really increase the amount of configuration you have to do. And, of course, it's limited to ISPs that have somebody to default to, so the transits themselves can't do this. But, if this means not having to buy a bunch of new hardware, it might be worth doing, and people do it. So, and then I'm aware of some cases where people do some rather sophisticated things to mitigate the non-optimal routes that come from just sort of blindly defaulting to your transits. And one thing in particular, there's something that I saw a couple years ago that Swisscom does, which is that they just define a bunch of what they call semi-defaults. So these are still defaults, still large aggregates, but they sort of pick them in such a way that most of the packets that would go to that default are in fact going to the best transit provider that they would normally. It's again what it is. It's still extra configuration, but if you're up to that, I guess that's okay. And in the end, I think it boils down to sort of a trade-off between your RIB or FIB size and the sort of AS path quality that you end up with. And for instance, the Swisscom reports that they get very good paths for most of their traffic, and they get about a 50% RIB-FIB reduction out of this exercise. So this is sort of a snapshot of what happens in practice. And what I'm going to talk about today is something that I think extends this. It's called virtual aggregation, and it's something that is being pushed in IETF these days. It's a working group item in the GROW working group. And I think the sort of principal people pushing this are myself and Xiaohu Zhu from Huawei. But you can see the list of other people that are involved and the organizations that they're in, as well as here a list of the drafts that are currently active, most of which will become 01 drafts in about a week. The main one is this first one that I have listed. I should use this. This one here, it's draft IETF GROW VA00. And this gives most of the information, and these other drafts are sort of ancillary drafts that talk about specific tunneling approaches and so on. So, so let me get into this. So virtual aggregation, fundamentally, it's a way to control the fib size in routers. It can give you really very tight control over how big the fib is in any given router. And it applies to the global routing table. It's not going to help you with your VPN routing tables, but it will help you control the DFZ routing tables. And also, it does not shrink your fib. Actually, one of the key reasons why this thing works as easily as it does is that it lets VGP run normally. It lets the ribs populate normally, but it shrinks what goes into the fib in a way that I'll describe pretty soon. It doesn't require any coordination between ISPs. A single ISP can decide to do this and get the benefits out of it without having to look like they're doing anything different at all with respect to their neighbor ISPs. And when I say works with legacy routers, what I mean by this is it works with some number of your routers being legacy routers and not upgrading to do virtual aggregation, and other of your routers being routers upgraded to do virtual aggregation. But to the extent you have legacy routers, they have to operate with the rib and the fib that they operate with today. Okay, so I mean, I say important today. It's actually an open question for me because, I mean, I know a lot of ISPs do things to extend the life of old routers, but I don't really know to what extent they would need something that's a little bit more general and a little bit more clean like virtual aggregation in order to do this. But what I do think is a bit scary is that, you know, given the exhaustion of IPv4 and the possibility that that's going to erode the quality of aggregation that's out there, and, you know, the uptake maybe someday of IPv6, fib size could become a more critical issue in the not-too-distant future, and you could indeed have fairly large ISPs that are finding themselves coming up fib-challenged, who might rather do something like this than upgrade all of their hardware. Okay, and so in my mind, VA is, if not important today, it's maybe kind of an insurance policy that if we do run into substantially larger routing tables in the near future, this might be something that eases some of the pressure that's on the installed hardware base. So I guess like everything, virtual aggregation is not perfect. Perhaps one of the main problems is that it requires some amount of configuration of its own. Whether this is worse than the tricks people do today perhaps remains to be seen. And the second is that it really, in the end, it entails a trade-off between how big your fibs are, or you know, how much fib reduction you get, and your traffic load. Ultimately, what you'll see virtual aggregation does is it slightly reroutes packets to another router that has the routing information that's needed to tunnel the packet to its appropriate exit point. And so some number of packets will take an extra hop in your network, which means you'll have extra load. In studies we've done, this trade-off is quite good. We could get, for instance, at least a 10 times reduction in every router in a fairly large ISP with virtually no increase in load or latency. But you know, this was an academic study, and it was a bit sophisticated in nature, and it's likely that people would do much simpler things in practice. So while these numbers seem fine, it's hard to know in practice if that's what we'll see. I mean, this is something that we hope to experiment with, and is partly why I'm talking to you guys today. So yeah, hopefully this timing is, the timing of this talk is good. It's fairly early in the process in ITF. I mean, it's been kicking around for more than a year now, but it's really only now at the point where it's an actual working group item, and there's still plenty of time to change the direction of things a little bit, or to add some experimentation or whatever. So primarily I'm here to get feedback from you guys as to whether this thing is, first of all, interesting or not, and if so, you know, maybe work out some of the details. And, you know, as a sales pitch, I'd be delighted if you thought this was cool and wanted to encourage your vendor to do it, but that's another matter. Okay, so let me talk a little bit about the technology itself. Is there a question, or? You thought I was done?
It seemed like you were about to open to questions, but.
I see, because I was asking for them. Funny you would come to that conclusion. We'll get there. So anyway, let me just give you the basic technology idea. You define in this something called virtual prefixes. So these are prefixes that are not physically aggregatable given today's topology. So you can think of these as /6s or /7s, or even in many cases just as simply as /0. And then within an ISP, you'll assign different routers to be responsible for different ones of these virtual prefixes. Ideally, it's done in such a way that in every POP there's a router that covers every virtual prefix, but that's not always possible. And then you run things so that a router either knows how to route a packet to a destination, or it knows how to route a packet to a router that does know how to route a packet to the destination. And all of this is done through the magic of tunneling, which there's a million ways to do in the internet these days. So as I said, this is really a fib suppression technique. So BGP runs as normal. So there's really no changes to the way BGP runs. Everything we know about making BGP run correctly still applies. And in fact, routers have full ribs as well. And so if that's the bottleneck for your router, this isn't really going to help you. But it does make it extremely easy to reason about the properties of virtual aggregation. So what happens is you run BGP as normal, and through these tunneling tricks, you're allowed to just sometimes not put prefixes into the fib, and this is done very late in the process. So pretty much your control plane operates as normal, and then just at the point where you would normally load a prefix into the fib, it's suppressed and not put there. Okay, so let me try to make this concrete. So this is obviously a toy diagram of an ISP, just enough routers to get the ideas across. As I said, in practice, the mechanism I'm going to show you would happen within a POP and not, well, I don't even show POPs here. So, all right, so here I've got an ISP. This one on the left, this AS with virtual aggregation, and a couple of neighbor ASs that we're peering with. And like I said, you basically divide your routing space into virtual prefixes and then assign routers to be responsible for these, and I call these aggregation point routers. So in this example, we have a virtual prefixes which is 22/8, and this router here, APR1, has been assigned as the thing responsible for all of the prefixes within 22/8. So among other things, what this router will do is it will fib install all of the prefixes within 22/8, and then it will announce originate a route to 22/8 with the next hop as itself. Okay, and I lost the pointer thing. This router on the left, it says here it's not an APR for 22/8, and so that means this router can actually not load into its fib all of the prefix within 22/8. So it gets to save that fib space. Okay. So just for a fraction of this example, this is the kind of routing information you might see. So if we look at, there we go. If we look at APR1 here, I showed this one routing table entry, which is how to tunnel packets to one of the networks that are within 22/8. If you look at this router on the left, I have an entry that tells it how to get to APR1, which is the router that knows how to get to things in 22/8. And finally, I have some information at the egress router here. Oops, I didn't really want to do that. At the egress router, which actually tells it what to do with packets that it receives on a tunnel. So basically, ASBR1 on the right knows that if it receives a packet on tunnel A1-1, it has to send it to ASBR2, and if it receives a packet on tunnel A1-2, it just needs to forward that packet to ASBR3. So this is just, not a fib lookup. It's just basically a tunnel mapping. There's an incoming tunnel, and it forwards it to another router. And actually, mechanistically, this can be done with penultimate hop popping in NPLS. Okay, wow. Really jumped. So how would a packet get routed in this case? So let's imagine that a packet arrives from outside into R1 on the left, destined to 22.1.1.1, which is within this virtual prefix that we've been talking about. R1 will look into its table and see that this packet has to be tunneled to the APR. And so it sticks that packet on a tunnel, which goes through R2, which is detunneled at APR1, which then looks at the destination address. And if you're wondering, the purpose of this tunnel is actually just to deal with legacy routers but it does turn out to be necessary. So APR1 looks into its routing table, sees that for this particular prefix, it has to tunnel the packet effectively. Well, it sees that the next hop is ASBR2 over here, the external peer, and to get it there, it needs to tunnel the packet on this particular tunnel A1-1. The packet is tunneled to ASBR1, who detunnels it, and then looks in this table and says, well, anything arriving over tunnel A1-1 has to be sent to ASBR2, and so it sends the packet as it should. So you can see from this example, the only router in the whole path that actually needed to know how to route that packet was APR1. Everything else, well, the Ingress router, of course, got it to APR1, but everything else basically just forwarded a tunneled packet based on the tunnel itself. Okay, so that's the basic mechanism. It works with MPLS pretty much as it is today, just using mechanisms that are used for VPNs. But, you know, especially given all the stuff that's going on in soft wires, it can be used with IP tunnels, GRE tunnels, and so on. So one thing to point out here, and this is intentional, is that that packet actually took sort of a longer path than it had to. I mean, you look at this, and if at least you're counting routers, you might think it should go through the APR2 on the bottom rather than the longer path on top. So in practice, you know, you might see a 1 or 2 hop penalty, typically within the POP, but it could potentially be between POPs as well, for tunneled packets like this. And that can be dealt with, and that can actually be dealt with quite nicely on a sort of per prefix basis. So basically, taking the same picture, there's no reason that we can't put a little extra information in R1 if this is a packet that we don't want to force to take that extra path. So this is something that we call popular prefixes, and I show here with R1 that we've added another entry, which is in fact the actual entry for this prefix 22.1.1/24. And in any event, the RIB knows that this has to go as a next hop to ASBR2, and so it's just a local matter whether this ought to be installed into the FIB or not. And that could be done on a policy reason or because, you know, there's a lot of traffic to this destination, and so you want to take it shortest path internally or whatever. But in any event, this information has been loaded into the FIB in this example, and then packets can be tunneled to ASBR directly from the Ingress router and then forwarded to the destination. Okay, so that's the mechanism, and again, we've standardized this for MPLS using LDP and just normal VPN operation, IP and IP and GRE in different specs. Okay, so that's the mechanism, and you know, partway into this work, Robert Restrick from Cisco got involved because he saw a particular deployment style that he thought would be quite beneficial. And so, and I think he's right. I think this would probably be a typical way that this would be deployed, especially early on. So I wanted to talk about it a bit. Yeah. Okay. So this is a kind of typical POP structure, and probably most of you with ISPs are running POPs that look more or less like this. So you have your PE equipment, your customer PEs, mostly, or PEs attached to peers or providers for that matter. So these are your externally facing routers. Internally, you've got some P routers that are simply running as a core for you. And then you've probably got some route reflectors that interface with this core and all BGP peer with each other. Okay. So with a structure like this, you can already do a fair amount of FIB reduction in 2 kinds of your routers. So your customer-facing PEs, like I said before, you can do FIB and RIB reduction just by defaulting them to the to the core and just not giving your customers the full DFZ. So again, this is done today quite frequently, and it's quite effective. On the other side of things, of course, your core doesn't need the full DFZ either, because your route reflectors can simply peer over the core and use tunnels to get packets across the core. So you can get a lot of FIB reduction there. And it's really the routers in between, or the routers that face to peers or providers, where you can't do this as easily. So Robert's idea is the following, is that you simply use your route reflectors as the APRs. And I guess I mentioned this in a way because when we did this as research, we sort of could do this with every router in the network, but Robert looked at that and said that's kind of silly. You can just do it at the route reflectors. And part of the advantage here is that in any event, this is where you typically do your configuration and so on. So it makes a lot of sense. Okay, so your route reflectors are your aggregation point routers. They know how to route to everything, either each one itself by virtue of just making it a /0 or to some fraction of the destinations. And then at your provider equipment, whether it's attaching to a customer or a peer or provider, it doesn't matter. You can do this in any of them. You only fib install routes for which that P is an egress, and that prevents the PE from sort of tunneling the packet back to a route reflector, which just tunnels it back through the egress. So you save on some potential extra load and latency there, and that can be done automatically. That doesn't require new configuration. And if you're happy to run your route reflectors with full fibs because they're modern routers, you can do that. And in that case, really all the packets in your network will be shortest path with what I just showed you. And so you don't need to deal with this notion of popular prefixes at all. If you want to do fib suppression in your route reflectors, then you'll have a case where it would be beneficial for your PE equipment to know the shortest path for your high volume routes. And so then you have to look into configuration of these popular prefixes. And we're looking at ways to do that in the GROW working group, but that's very, very early work at this point. All right, so I've given you, I guess, the mechanism and sort of the deployment strategy. And I guess from your point of view as a network operator, this is sort of what you have to do. First of all, you have to look at your network and figure out where you want to do fib reduction, where you want to extend the life of older routers. Based on this, you design what your deployment's going to look like. And again, it may very well look like what I just told you, but you decide what your VPs are going to be. And it might be simply a single /0 if you can keep the full fib in all of your route reflectors, or it might be /6s or /7s or something like that. You configure your routers as APRs. You configure what's called a VP list in all the routers, and this is just some static information that tells them what the VPs are so that they know what they can and cannot fib suppress. And if you're not doing fib reduction in the route reflectors, you're kind of done. And if you are, then you need to figure out which prefixes you really want to take shortest path and configure your PEs with that information. And that's sort of the nasty part of all of this. And again, we're looking at how to automate this. Yeah, okay, so basically done. So to summarize, this is new work in IETF GROW. It's early in the process, so I think there's a lot of scope for influencing this. And if this sounds useful to you, please let me know or participate or whatever is appropriate. Oh my gosh. I think we're out of time. I go now.
Hi, my name is Frederick Gilmore. I'm from Akamai Technologies. And this is not meant as a detriment or anything, but it seems very, very complex.
Yeah.
And I was wondering, we were actually having a little discussion. One of the things that we've always asked that seems a lot simpler is if you just take prefixes out of the fib that are covered by a shorter prefix that has the same next hop. And we can't seem to figure out how much that will actually save. Some people say 5%, some people say 30%. But that seems like a quick, easy, simple way to not have packets travel over tunnels, not configure tunnels, not go through suboptimal paths, and still save your fib. Have you looked into that in any way?
So I haven't personally. I mean, I know what you're talking about. I know people have. And maybe Lisha Zhang, if she's here, knows how well that works. She's coming back there.
Well, I mean,
but
operationally, it's an equivalent thing, right? The only question is how much coding effort there is to make it work properly.
And how much reduction you get out of it.
Yeah.
Yeah.
So, I mean, one of the guys behind me has actually studied his router, and it's far greater than 5% reduction. So maybe that would be a better way to ask the vendors to do things to start with, and then we can do this if that doesn't work well enough.
Yeah, maybe very well. Lisa, you want to comment, or are you just?
I hate to jump the queue, but sure. So it's actually not me, but the two other guys, Lan Wang and Bichuan Zhang in my team, they actually did some data digging and figured out that you could compress the FIB just by the way you talked to 30 to 50% or even 10%, depending on which router you're talking about. Further to the edge, you have lots of sharings of the next hop among the prefixes, but further into the core, maybe less so. But 50% is like kind of the lower bound. I mean, that is at least you can compress to 50%. And they had a nice scheme to handle the routing changes. That is, just in case your next hop actually changed, they have a very graceful way to deal with that. So I would be, actually, we plan to give a talk that girl in Hiroshima.
Yeah, and in fact, I was talking to Alicia this morning about this, and it makes perfect sense. I mean, if you have something that's simpler than what I'm talking about, that, buys you another year or two, by all means.
Hi, this is Donnie Roisman from Peak Web Consulting. Thanks for the topic. Much like what Patrick was saying, I remember one of the NANOGs, we were asking our vendors for this right around the time we were exceeding 200,000 routes in the DFZ, and a lot of our hardware was going to fall over shortly after 200,000 routes in the FIB. And I remember hearing some vendor comments, which was pretty much, well, we're not going to fix it in hardware when we can make you buy more, or sorry, we're not going to fix it in software when we can simply make you buy more hardware. But it's pretty unreasonable. We have clients that are pushing 1 to 3 gigabit per second and want full routing tables, and they're not going to spend $50,000 on routers. I had one quick question for you on slide, I think it was slide 16, where you were showing your toy network there. Mm-hmm. Yeah, the question right there. That's enough. Which of those routers do need to be capable of carrying the full table?
Yeah. So in this toy thing, none of them do, right? So for instance, APR1 here has all of the prefixes for 22/8, but some other router could have the ones for 23/8 and some other ones for 24/8. So the study we did on a large transit ISP was that all of the routers did it, and the router that received the least savings had a 10 times FIB savings, and other routers had actually much more. But again, that's a rather sophisticated and potentially unrealistic deployment. So, yeah, we're not.
Okay, yeah.
I mean, we need to work with people to figure this out a little bit.
It seemed to me operationally there were a lot of routers involved here, and it would be nicer to not have to add more equipment, but to have software that can do. Like
this is completely software based. There's no new equipment here.
Okay.
These would be the routers you have anyway.
Okay.
But with a software upgrade to do this.
Okay, thank you. I appreciate the time on the topic. Thank you.
Thanks.
So in the case where, Owen DeLong, Hurricane Electric, and also here in AC, in the case where you already have all of these different routers everywhere, and you have 10 routers in a POP, that might make sense. But looking at this from the perspective of an ISP that usually has about 2 routers in a POP and still manages to run a fairly large backbone, this to me looks like just a more expensive way to distribute your CAM load across routers that don't have enough CAM and have multiple routers pretending to be one router rather than having enough CAM on the line cards.
Yeah, there's an element of that.
Hi, Richard Steenberg at NLayer. So I can provide a little bit of operational experience here. How many people remember the Foundry big iron boxes, the old Iron Core, that had like a CAM of 8K back when the routing table was a little bit bigger than 8K? And they're the only vendor that I'm aware of, major vendor, that solved this with software aggregation. They had 2 mechanisms. One where you just had a default route, it would just aggregate it down to 1 route. Sure. And 2 where it's still, if you had a default route, it would break it up into like /12s or something, so it would like fill up like 4K worth of FIB. And that was surprisingly effective at aggregating. What you're talking about in terms of how much aggregation savings you get depends on how many next hops you have, right? So if you have 1 uplink, you're going to aggregate down to one route. If you have 2, 3, 4, 5, 6, I mean, how many paths from any one router do most people have in their network? And I guarantee you the answer is not 300,000. So you really there's a huge potential there, and I think it would really work out well for vendors to start looking at that as an alternative to this, because what this reminds me of, I knew someone who once built a ring of 3550s where it had to default to the next one, and he fed it with like partial routes from like a zebra router, so if it didn't have it in the one, it'd go to the next, and that to this day wins my award for most ghetto routing. And that's what this reminds me of, and I gotta say, the tunnels, I can't see myself ever deploying that.
Yeah, okay.
Igor Gushinsky, Yahoo. I'd like to echo Richard. Yes, you can save on fib size. Yes, it's probably cheaper to just buy bigger routers because you're also giving up a lot of slot density in order to interconnect all of those in order to actually carry the bandwidth. So you may not be winning much. Doing some sort of fib compression seems like the much better route to go.
Yeah, I actually did want to mention this back here. I mean, these tunnels, they could just be, automatically configured LDP tunnels, right, for all that matters. So it's, they are there, but it's not like you have to manually set them up or anything. Yeah.
Anton Capella, Voxel.net. I think we spoke earlier this year, Paul, about BGP stuff. It's good to see you working on this domain as well. I'm curious if you considered or had any chance to work on answering the question or questions of what could this mean for auto TE, QoS kind of stuff internally when in particular label imposition or label swap requires examining EXP and copying it to perhaps a new label or features that we don't have today. Has that been part of perhaps the investigation into practicality?
I have to confess I don't understand your question.
Okay. Well, so if we're going to be redirecting packets between various routers and kind of what I see as a confederation of participants in virtual aggregation,
yeah,
it means something for the link loading, certainly. And if I want to reserve some amount of traffic, but no more than some % of the whole link,
yeah,
for class, it would seem to have to somehow transport that in a new way to not overbook things inadvertently.
Yeah. So that's sort of the danger of describing this thing the way I do. It looks like you're moving a bunch of traffic somewhere. I mean, I think in practice, when you do this, there's very, very little traffic that actually takes the extra hop, either because you've configured it more or less in the way that I described, or because you exploit popular prefixes to the extent that, the vast majority of your packet is actually taking the shortest path anyway. So, if that's the case, then it doesn't really change your traffic engineering much because your packets are actually following the normal path anyway.
And as a follow-up to that, does the popular prefix idea have a better, fuller description in your papers or anything I can read about? I'm curious about how that would work.
Yeah. So there's the drafts and
okay. It's described there.
And there's an academic paper by this guy Balani and myself, and you can just Google for that.
Thank you.
Thank you.
Okay, thanks. If there are no more questions, thank you very much.